In this video, we're going to work through an example focused on an absorption process and use what is known as the McCabe-Thiele analysis for these kind of dilute absorption problems. So here we have a process that's releasing chloroform into an airstream. And so we have air at a certain flow rate with a certain concentration of chloroform, and we'd like to reduce that to a more permissible level. So the question asks, how many stages should be designed into this column to reach the extent of absorption that we would need? First place to start is with a diagram or a picture of our process. Here I've drawn an absorption column. We have an entering stream here of gas, or in this case our airstream containing chloroform. We have gas leaving our column. We are pumping liquid, in this case water, to the top of our column so that it flows downwards and we get our liquid leaving the column. Let me fill in some details that we know. So we're given a vapor flow rate of 1,000 kmols an hour. We're given an inlet concentration of 200 parts per million, which is a mole ratio, but since we're working with really dilute solutions, we could write it as a mole fraction. So our mole fraction of chloroform entering is 200 parts per million. So for every million parts of air, we have 200 parts of our chloroform. We're also told the concentration leaving needs to be 10 parts per million. Since we're using pure water, we know the concentration coming in of chloroform in the water stream is 0, and that's all we are given. We're asked to determine the number of stages for this column. So the question now becomes, is this something we could solve? We could use a degree of freedom analysis, and for a single section countercurrent cascade, our degrees of freedom will be equivalent to the following, where n is our number of stages, c is our number of species. So at this point we need to make some assumptions so that we can minimize the amount of variables that we may need to find or look up. If we say that each stage operates adiabatically and there's no pressure drop along the column, then we'll fix the amount of variables equivalent to the amount of stages times 2. Looking at our incoming stream here, it's completely specified, temperature, pressure, composition, and flow rate, therefore taking C plus 2 variables up. Now for our liquid feed, we are told that it's pure water, but that is about it. So we could assume that the entering liquid is also at 25 degrees, but we are not given a flow rate for the liquid, so we only fix C plus 1 variables. If we take into consideration how many we could fix with our assumption and how many we are given, and compare this to our degrees of freedom for our absorption column, you can see that we are short one variable. And as mentioned, this is going to be our flow rate of our liquid stream. So we need to make another assumption. The flow rate for an absorbent can be related to our L over V min. So a good operating condition for our absorbent flow rate is typically somewhere in the ballpark of 1.4 times the minimum absorbent flow rate. So we're going to assume that our flow rate L is going to be 1.4 L min. So we need to figure out what that minimum flow rate would be for our system. Typically a good ballpark range here is between 1.1 and 2 times that minimum flow rate. Now we've specified L prime and we can find L min. One more major assumption we need to make in this case is that since we're working with very low concentrations of chloroform, that we are going to assume that no water is stripped into the gas stream and no air is condensed into our liquid stream. That being said, our flow rates for our liquid and vapor will be constant. And lastly, because we're working with very dilute solutions, typically for an absorption problem, we would be using Y or big X to signify mole ratios. But these can be approximated by the mole fractions since we're at very low concentrations. In this case, as our mole fractions approach 0, our mole ratios approach our values for the mole fractions. So we can plot for the McCabe-Thiele diagram just in terms of the parts per million as our mole fractions. And lastly, the only thing we need left, not an assumption, but is to pick some kind of phase equilibrium information for this system. And in this case, with chloroform at the concentrations we're using, we can assume Henry's law, which we could look up for this system in a handbook and see that chloroform has a Henry's law constant of 211.19, and this is atmosphere per mole fraction, in water, 25 degrees Celsius in 1 atmosphere. So using Henry's law, we could figure out what our phase equilibrium line is going to look like. In this problem, we've looked up Henry's constant, and we know the pressure that our absorber is going to operate at, so we could get a relationship between y and x. So you can see this is a straight line with a slope of 140.8 that goes through the origin. So we could plot this on a y versus x plot along with our operating lines. So for our operating line, we want to work in the appropriate region of our concentrations. So to determine the extent at which our phase equilibrium line extends, we could take the concentration that we start with, the 200 parts per million, and divide it by our phase equilibrium slope. The concentration in the liquid phase will be at equilibrium. Based on our column, we know exactly what one of the points on our operating line will be. We have x0 equals 0, and we have y1 is equal to 10 parts per million. So the top of our column, or the bottom of our operating line, will go through the point 0, 10. So here we have a plot that we can start working with. Obviously you can see that the y and x axes are not equal. We do know that the equilibrium line at 200 parts per million for y will be 1.42 for x. So that puts us right about here, and we know it goes through the origin. So this is our phase equilibrium line. We also know that the bottom of our operating condition is going to be at 0 for x and 10. So if we wanted to determine at this point what the minimum absorbent flow rate would be, right? We're looking for L min. That's going to correlate with an infinite amount of stages. So this is what our operating line would look like if we had an infinite amount of stages counted off between our operating line and our phase equilibrium line. As you see, that gap becomes smaller and smaller. So we could determine what the slope of this line would be, because that will give us an idea of what our L and V ratio is, and then we can multiply that by our factor 1.4 to draw our actual operating line. So in this case we have 200 minus 10 for our change in y, and we have 1.42 minus 0 for our change in x. We get a slope of 133.8. If you recall, our operating line for an absorber is y equals our ratio of our liquid to vapor flow rate times our composition in liquid phase plus our other conditions, both leaving and entering our column. So the slope of this line is L over V. So we've now determined L over V minimum as 133.8. And we want to operate at 1.4 times L min, and that gives us 187.3. And we can plot a new operating line through the same initial point at 0, 10 with a new slope of 187.3. So using our ratio 1.4 to the L over V min, we could plot our actual operating line for our system. We could solve for xn in this case and see that it is about 1.06. So now that we know our outlet condition, we have our operating line, our phase equilibrium line, we could start counting our stages. So we start at the conditions for the top, which are down here. We go exactly horizontal over to our phase equilibrium line. We go straight up to our operating line. That's stage 1. So we'll have the vapor stream Y2 crossing the liquid stream X1. Then on stage 2 we go back to the equilibrium line. And we continue this process until we get to the desired absorption stated in the problem. And you can see we would need around 7 1/4 theoretical stages. Of course we have to have a whole number, so we'll have 8 stages to accomplish the absorption that we need to, so that we could release the vapor with 10 parts per million when it starts at 200 parts per million. So that's how we work through an absorption problem in determining the amount of stages that we'll need. Recall we did have to make an assumption about the flow rate of the absorbent that we were using. It's also important in this question to notice that our concentrations in the gas phase are still much higher than those in the liquid. So the physical absorption of chloroform into the water is not necessarily a great way to go, but if you were stripping it from water into the air, that'd probably be a pretty good process.